Hi, my name is Bill Fortney, and once again, thank you for joining me with Probability and Statistics for Engineers. By now, you should have gone through session 1 through 5, where you got a foundation in basic statistics and how we do probabilities. Now, what we're going to do is turn our focus and start looking at real world data analysis, because there's a lot of complications when we actually go to do this that you need to be aware of to do this successfully. Okay, so let me start off with just looking at what do we really do as engineers? What do we really do? We solve problems. To do that, we make decisions. And when we do that, it impacts money and it impacts lives. That's really what we do. We spend money and we impact lives by solving problems. And to do that, we need to make decisions. So we do this with facts. You've been in school long enough to realize that engineering is all about fact-based decision making. So for a good decision, we need good facts. So how do we get good facts? If we need facts from a person, we go and talk to them. And dependent upon their answer, if it seems a little uncertain, we may go and talk to someone else. And we continue to talk until we have that warm, fuzzy feeling that we have good, solid information that we can use to then do our analysis or whatever to make a decision to solve the problem. If what we need information from is a thing like an aircraft engine or a part or whatever it is, then we may be able to go research and get some information, but very often we need to go and collect data. We need to ask the thing, what can I expect from you? And the whole first series dealt with that from a when things are nice standpoint. So for us, we measure and analyze data to gain reliable information. And that's key, reliable information. You're going to see that that's not an easy thing to base a decision for solving a problem. And you always want to keep this in mind. How good of information do I need? You need it good enough for the problem that you're solving. Depending upon the seriousness of the problem, the level of accuracy, et cetera, depends upon the information, the reliability that you need. So you always want to keep this in mind that that's what we're doing. We've been focusing where we've been given data and we focused on analyzing it to answer that question, what can I expect from you? And you've seen this diagram time after time, and that's what the first 5 videos really focused on. So I'm going to review that real quick and then jump into showing you the real world aspect of it. So you remember the example that we had, our factory makes the bolts. Our boss wants to know if he's going to jail or not. So we went and we took data. The first thing we did is we said, why are those two different? And we were told they're different just because. There's variation in everything. We understand that. And all those work together, in this case, to create common cause variation or random variation. So what number do we use for a decision? We looked at some statistics. We said, well, we can't use the minimum because we don't care just about these 30. We care about everything. And that's when we said, okay, if there's common cause variation, the numbers we collect are random variables. They follow a predictable pattern, the probability distribution, that tells the likelihood of the different values occurring. So that probability distribution is described by its shape, central tendency, and spread. And one example we worked with was the normal, where the value is down at the bottom. At the top's the probability that it will occur. And we even saw through the Galton board how distributions actually happen in the real world. There's a lot more paths through the factory to get here. And so we saw that that's how we can't know an exact value, but we can predict a pattern. And then we said, okay, so if the process is stable, common cause variation, then there is a population, our factory. It has a distribution. We assumed normal with some central tendency and spread. And now we want to know what can we expect from our factory. So we're going to take a sample from the factory to estimate the population parameters. We'll do that using the sample statistics. And then once we do that, statistics can tell us what to expect. And we saw for the normal, it's really convenient because what we can expect is based upon how many standard deviations we are away from the mean. And so we saw this generalization, and then we saw, you know what, we can actually calculate an exact value for the normal for whatever we want to. And we did that in our case to see what the probability was of getting a point below our standard and found that it wasn't good. And then we also found how we could adjust our average so our boss wouldn't go to jail. But with this information, we then said, okay, let's look at three factories that are all normal with an average of 81, but different standard deviations. And what can I expect? So we saw here's one with a standard deviation of 2. We saw a standard deviation of 0.5 and then a standard deviation of 0.1, three different factories. And we pointed out a couple of things here. One, the impact of standard deviation. Variation is not our friend because the more variation, the wider the range is for me to say, what can I expect from you? Well, you could expect anything from 75 to 87. What can I expect from you? Well, it's going to be between 79.5 and 82.5. The other thing that we pointed out was it's reasonable to get any number in this range. You know, we think of the average. Oh, no, we can get any number in that range. And then that brought us to the idea that the average is not the whole story. In fact, hopefully that you see when you're talking about what can I expect from you, the answer is never a number. The answer is a range, and then you've got to decide what to do with that range based upon the decision that you're making. Okay, so that brought us to what number to use. Well, we now know that because they're random variables in the distribution, we can know exactly what to expect. We can do ranges, we can calculate an exact probability like we did for your boss, figure out exactly where to crank the average, depending upon how certain we want to be. We don't go out of that range. And so we've learned that with statistics, we can know a lot about what we can expect to help us make decisions. That's what we've done so far. Now, in the real world, though, we have to get our own data. Over here, we were given the data. The real world, we've got to get our data. We have to measure and obtain reliable information before we can analyze and ask, what can I expect? And I'm just going to say that measurement is hard. And the more you do it, the more you grow in your engineering and you're taking measurements in the real world, the more you're going to see it is really hard to know that you have reliable information. You have a reliable measurement of what that real value is. But everything rides on the validity of data. Over here, we could tell you exactly what to expect, but we were counting on the data being reliable and accurate representation of what was really happening. And you're the one that's got to ensure the data is valid. So now that we're in the real world, it's not just doing the number crunching that we learned over here, which is really important. It's learning how to measure and obtain reliable information. And that's what we're focusing on. And so in here, I want to put you in this real world situation where now you're the one that your manager's coming to. And he says, look, keep me out of jail. Tell me, what can I expect from this? So you've learned now, so you go, you've got your population, you take a sample from it, you then create a measurement system, and you measure those samples. You then calculate sample statistics from those in order to estimate the population. You use what we've learned from the distribution, and you make a decision, you give your boss an answer, and you're feeling pretty good. And then you go in and you tell your boss, and then your boss wants to know, first of all, is the process stable? Because this whole time we've been assuming that it's stable, only common cause variation. He said, well, was it? And you may or may not know. And if you say yes, he's going to say, well, how do you know? And you're going to need to be able to give a defense. And if you can't give a defense, then she is going to say, you're telling me I'm not going to go to jail, but you don't even know if the process was stable. He's also going to ask you, Does this sample that you took appropriately represent the population? And you're going to be like, huh? And then the last question he's going to ask is, do these measurements estimate the true values well enough for the decision being made? Did you pay attention to your measurement system? And again, you're going to have to answer those. And if you can't answer them and answer the challenges that they will give, you go back to the drawing board. That is the reality of real world engineering decision making by getting information, because you're spending money and impacting lives. And your senior engineers, your manager is going to grill you to make sure that you've got solid facts in order to do that. That's the reality of real world measuring. And like I said, it's hard. You're going to have to be able to answer these questions. And success at doing this in the real world first requires you to understand two things. First, you need to understand that obtaining information from the real world, measuring, is always an experiment, and it must be carefully planned and executed. And you've heard about experiments. In Nathan's lecture, he told you an experiment is using the measurement process to seek new information. He's got goals down there. So you're going to learn a process to plan, design every detail of your experiment. Use it. It is critical. He also talked about variables, the different kinds of variables. All of these types of variables can be present, and they can potentially be impacting what you're trying to measure to answer the question, what can I expect? And a well-designed experiment is going to properly address those so they aren't unintentionally influencing what you're trying to answer. Take your time when you're identifying these, because missing one variable that has a big impact on what you're measuring can make all of your results completely null and void. You may think it's telling you one thing where really it was this other variable that you missed that's causing it, and your results aren't valid and you're going to make a wrong decision. So take your time and pay attention to these. These things that Nathan is telling you, they're not academic. They are essential for real world experiments to get information to make decisions. Okay, the second thing you've got to understand, and when I say success first requires you to understand these things, you need to understand them and always keep them in mind when you're doing experiments. Let it override everything you're doing. Here's the other one. Analysis is not obtaining the answer. Over here, it was almost like we were looking for the answer. It was a math problem. But analysis is not obtaining the answer. It's listening to what the data is trying to tell you. And let me show you what I'm talking about. Where you want to approach analyzing data like a detective, not like an accountant. So you have something of interest, whether that's our factory, whether it's a circuit, whether it's a helicopter gear, doesn't matter what it is. And you've got items being measured, you're going to measure them, and from that, you're going to create data. Now, that data is like a radio signal. That data has many, many things to tell us, but we have to be curious and find the correct channel to hear what it's saying. Back in the day when radio was analog, you'd have a radio and there'd be static, and you'd turn the dial until you got on the frequency for a particular station. All of a sudden you'd hear something. You kind of get the same thing today with digital, but you don't get the static. You're either on a station or not. So you still change it and hear different things. Well, that data, it's like it's sending you all this information that it's trying to tell you you've got to get on the right station. So looking at the data in different ways is like changing the radio station. You can graph it different ways. You can do different groupings of it. You're going to look at the data in different ways. And when looking at it different ways, we stay curious and we're always looking for clues. We're looking to see what's the data trying to say, And what's it trying to tell us? And sometimes we change the channel and we find a good station. We learn something of interest. And a lot of times that will lead us to then dig deeper, explore other things. Sometimes we change, we graph the data a certain way. We don't hear anything, we don't learn anything. But as good detectives, we stay curious, we follow the leads, and we keep trying until we learn everything that data has to teach us about the thing of interest. That is what will make you a good engineer and will help you always make good decisions. Let me just give you two quick examples. I'm not going to go into details of the situation. I just want you to see what getting on the right station can do. So we were interested. We're a factory. We make parts, and we have 5 different methods of measuring a 10-inch part. There's a part that's supposed to have a 10-inch diameter. We have 5 different methods. We wanted to know how much uncertainty there is in those 5 methods. So we had a gauge block. We measured it 10 times with each method. And here's the data, method 1, 2, 3, 4, and 5. And one way we could have graphed this, which is very common, is you just graph each column right there. And we can see some things about this. Here's 10. So you can see these two, you can look down here and see the methods. They're pretty much on 10. This guy's high, these guys are low. But now, let me change the channel and see whether the data is trying to tell us anything different. To do that, I'm going to change the orientation of the data. We like to orient data this way because it's real easy for our eye. What you're going to find is from an analysis exploration, it's often much better to have your data going down this way with your different categories, and then you're going to be able to group and look at your data based upon all these categories here. So I do that first. Here is the original one. Now what I'm going to do is I'm going to do a line graph with it just plots points in order. So here's a line graph. All it's doing is coming all the way down here and plotting them in order. Whoa, I don't know about you, but to me, whoo, it starts speaking really loud. The fact that this is high and these are low stands out like a sore thumb. The other thing that stands out like a sore thumb is this guy has a lot more variation than this guy. It's bouncing around a lot more. Now, let me say, and I'll hit this again later, but from a practical standpoint, this would never happen in industry because they would be calibrated. You learned in the lecture about systemic error, about bias. These are biased. Those devices need to be calibrated, whoop, 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 and they would all be in there. Okay, let me change the channel again. This time I'm going to do an XY graph with method being my X and that being my Y. Looking at it another way. Now, for me personally, I think this shows the difference in variability a lot better than the other ones. But again, the point is, we're going to come back to these, but the point is changing the channel can show things differently. Here's another one. We were interested in what glue we should use when we're gluing PLA parts. So we had 3 glues, we got parts, we glued them a specific way. I'll go over this whole thing later when we talk about design of experiments. And then we got the data and then we graphed them. Again, I started with sort of what I call the standard graph where this data was in columns, and so we plotted each one. So there's one glue, there's another. And again, I can kind of see that whatever PW was, it was not as strong. These guys looked pretty similar. Let me change the channel though. And you see these little boxes. That's plus or minus 2 standard deviations. I have which glue it is labeled right out here. And again, to me, the fact that these are really similar, except this one has a little more variation. Clear as a bell, that one's lower. Okay. But then this group, as good detectives, they were like, you know, this is interesting that these were both the same. And then they said, you know what? Some of these, the part broke, and some of these, the glue line broke. They added that to their data table, which I didn't show you, and then they graphed it again, and look at what they found. They found all of these, the part broke, all of these, the glue broke. They're detectives. They're not looking for one number. They're looking for what the data can tell them. And they're like, well, that's weird. They're both the same strength, basically, but the glue broke here and the part broke here. So they're like, I wonder whether this glue changes the chemical composition of the PLA and makes the actual PLA weaker. They're like, I wonder what just plain old PLA would do. They had one part that had not been glued, and they plotted it up here. So you see, they're being detectives, and they're like, okay, yeah, the fact that the part broke down here is not normal at all. We're pretty sure that this kind of glue changed the chemical composition of PLA. Yeah, we need to go explore that more. Okay, but you see, that's data analysis, where the data wants to talk to you and you need to listen. You need to change the channel, and Nathan will help you, and you will learn different ways to change the channel. But these two fundamental things, keep them in mind so that when you go and you tell your boss something and they start grilling you with these questions, you're going to be able to answer them, and you're going to make good, solid, sound engineering decisions. Okay, so why is measurement so hard? Why is it so hard to answer those questions? And there's really three reasons. Number one, there's variation in everything. We've seen that, and we're going to hit that just briefly. Number two, which is the biggest, is the thing that you're measuring, the population, it might be changing. It might not be stable. I use the phrase, the world is not a nice place. There's lots of things trying to change what you're trying to measure. And if they're changing it while you're measuring and you don't know they're changing it, you're going to think the data is telling you one thing when it's not telling you that at all. So we're going to have to learn how to deal with that. And then the third one is the fact that your measurements are only estimates of the real value. How good of an estimate? It's going to depend upon your design of your measurement system. And again, that's no easy feat. So what we're going to do is we're going to explore each one of these. We're going to do one video that's going to hit the first two, and then the last video is going to hit the last one, to just give you a foundation in these things so that you can take measurements, even when you're starting to do it in lab, and begin to practice these things for what you're going to need to do out in the real world. So the next video will hit these first two.